Same array, same question. One approach checks the array over and over, the other moves through the array in one clean pass, and finishes before the first one even gets going. This is the two pointers technique. And once you see it, you'll never brute force a sorted array again. In the next few minutes, you'll understand exactly why this works, how to spot when to use it, and how to turn an O of n squared brute force into a clean O of n pass with real Java and Python code. Picture a row of parking meters sorted from cheapest to priciest. You've got a friend, and together, you want to spend exactly $12, 1 meter each. Instead of checking every possible pair, you start at the cheap end, your friend starts at the pricey end. Too cheap together, you move up. Too expensive, your friend moves down. You're not scanning everything, you're closing in from both sides at once. That's the entire idea behind two pointers. Let's make this concrete with the classic version of this problem. Given a sorted array, find two numbers that add up to a target. Here's our array, 1, 2, 4, 6, 8, 9, and our target is 12. A brute force mind checks every pair. Let's see exactly how slow that really is. Brute force means checking every possible pair, index 1 against every other index, then index 2 against every other index, and so on. For 6 numbers, that's 15 comparisons just to be safe. Not terrible here. But double the array to 1,000 numbers and you're suddenly making 500,000 comparisons. That's O of n squared, work that grows as the square of your input. We can do so much better, and because we're throwing away the one thing this problem gives us for free, the array is already sorted. Here's the move. Put one pointer at the very start, one at the very end. Add the two numbers they point to. 1 plus 9 is 10. Our target is 12, so 10 is too small. Because the array is sorted, the only way to get a bigger sum is to move the left pointer forward. Every number to its right is bigger. So left slides forward, one full step. If the sum had been too big instead, we'd move the right pointer backward towards smaller numbers. Notice what we never do. We never move backward, and we never recheck a pair. Every move makes real progress toward the middle. Let's keep going and watch the rest play out. Left is now 2. Right is still 9. 2 plus 9 is 11. Still too small? Move left again. Left is now 4. Right is 9. 4 plus 9 is 13. Now too big, so this time we move right backward. Right is now 8. 4 plus 8 is 12. Found it. 4 steps, start to finish, and not one wasted comparison. Every single move brought us closer to the answer. Here's why this matters, and this is the worst case, the absolute ceiling. Brute force is O of n squared. The work explodes as your array grows. 2 pointers is O of n. Each pointer moves forward at most n times total, so even in the worst case, the work grows in a straight line. At 1,000 items, that's the difference between 500,000 comparisons and under 1,000. Same answer, wildly different speed. Once you see this pattern, you'll spot it everywhere. 2 pointers reverses an array in place. It removes duplicates from a sorted array using a slow and a fast pointer. It checks if a string is a palindrome by comparing from both ends inward. It solves container with most water, 2 walls closing in to maximize the water between them. And it's the foundation for 3-sum, where you fix one number and run 2 pointers on the rest. In Java, we call this method 2-sum sorted. The name itself is a reminder that this only works on a sorted array. We start left at 0 and right at the last index. While left is still before right, we compute the sum. If it matches, we return both indices immediately. If the sum's too small, left moves up. If it's too big, right moves down. If the pointers ever cross without a match, there's no answer, so we return -1, -1. Same logic in Python, same name, 2-sum sorted for the same reason. Just 2 variables, left and right, a while loop, and one if, else block deciding which pointer moves. No nested loop anywhere in sight. That's the whole algorithm. 4 mistakes that trip people up. 1. Running 2 pointers on an unsorted array. The technique depends entirely on order, so sort first. But here's the catch beginners miss. If the problem asks for the original indices, you can't just sort blindly. Sorting scrambles the positions. Either sort pairs of value and original index together, or switch to a hash map approach instead, which doesn't care about order at all. 2. Moving the wrong pointer when the sum is too big or too small. Always double-check which direction actually helps. 3. Using left, less than, or equal to right instead of strictly less than. That off by 1 lets a pointer check itself. And 4, the deeper one, forgetting why this works at all. It's the sorted order that guarantees moving left only increases the sum and moving right only decreases it. Break that guarantee and 2 pointers gives you garbage. Let's lock in the decision logic. Start with left at the beginning, right at the end. Calculate the sum. If it matches the target, you're done. If the sum's too small, move left forward. If it's too big, move right backward. Keep going until the pointers meet or cross. If they do without a match, there isn't one. That's the entire algorithm in 5 lines. You now know the pattern that turns O of n squared into O of n, and you can already reverse arrays, remove duplicates, and check palindromes with it. Next, we'll aim this same technique at 2 real interview favorites, container with most water, and 3 sum. If this made 2 pointers click, subscribe. Code clarity, data structures, explained visually.